The following podcast is a proud member of the Blue Collar Roots Network. Find all the shows by visiting bluecollarroots.com. And now, the man who takes the BS out of BS, Bill Spohn.
Hello and welcome back to the Building HVAC Science Podcast. It's our goal here to help create better, more knowledgeable HVAC and building performance technicians, helping the two professions to better understand each other with the ultimate goal of making customers happy in the homes they live in and the buildings they work in. Science, in pursuit of understanding in the moment. Join us as Rachel and Eric Kaiser, a husband and wife team from Indianapolis, share with us their perspectives on HVAC chemistry. If you've attended or watched Bryan Orr's HVACR School Symposium over the last 3 years, you may have seen them present. We discussed the relative scales of time and size, as well as the properties and impact of water on HVAC designs and decisions, and so many other topics. We learn more about the scientific and chemical aspects of dirt on surfaces, coatings, and filtrations. Some notable thoughts that came out of this conversation. Chemistry is like baking, only you shouldn't lick the spoon. Cooking is like jazz music, and its improvisational aspects. There's some links in the show notes where you can watch Ty Brenneman interview Rachel at the latest HVACR School Symposium. And there's also a link to some of the other podcasts that Eric has taken part in on a wide range of topics, from careers to tools to HVAC charging and more. In a special announcement, we're proud to announce that Eric will be sharing his knowledge and skills and working with TrueTech tools on a regular basis beginning in June 2022. So let's listen in as Eric and Rachel share with us aspects of HVAC chemistry. Welcome back to Building HVAC Science. Science with an exclamation point. That's what we'll be talking about today.
Yeah.
And I have two very merry people on the other end of the podcast system here, and that's Rachel and Eric Kaiser. Good afternoon.
Good afternoon, Bill.
Good afternoon indeed.
Rachel and Eric, you're a team. You're a team in life, but you're also a team in science and HVAC science. Rachel, tell me how this team got formed.
It did actually stem from the fact that we're partners outside of being able to talk about science as well. We've known each other Eric's entire life. So that helps really build a real strong foundation and actually ties exactly to the topic, because when you look at science, you have to start with a firm foundation or you're not going to be able to problem solve or use any advanced technique. So for us, I think it's the same. We have a really firm foundation, and from there, we're able to explore and look at other options of ways to not only educate between ourselves, but also share the things that we've learned and help educate others on a variety of topics, science being one of my passion spaces.
And Eric, we hear your voice on a lot of podcasts. You're doing some things with HVAC School. You've done a lot of different things in your career. But lately, the last couple HVAC symposiums, Rachel's come along and you've done some co-presentation there or individual. How did that go?
I think the last one, the one here in 2022, is the first one we actually did co-presentation on. Previous to that, we had both presented, but separately. And we talked about it and decided to try something a little bit different, primarily because we really wanted to be relatable to the technicians. And that's my niche, and where I fit in is being relatable, because I've done that. I've been there on a lot of things. So not saying I know everything or have done everything, but I've done a lot and enough to be able to relate. And Rachel is the very detailed science, in-depth person. And we have a good dynamic where we can work back and forth, and I can try to pull out some of what she's talking about and relate it to the HVAC technical people so that we get a good mix.
And we did that partnership piece even when you were in the field. There would be times that he would come back, or a few times that where you even called while you were at the piece of equipment, and this is what is happening, and usually chemistry related.
Yeah, very much. And it's a great resource for me. I'm very lucky to have it. And we're going to
phone a chemist. It's not really a service most people offer.
No. Rachel, let's dig a little bit into your background, your training, your experience, and what you do now outside of this HVAC niche.
I am the opposite of Eric in that I've been very formally trained as far as my education pathway. And so I think that also helps bolster our partnership. But undergrad, graduate school, all those pieces, and all of that had science as core areas. But I always tied that with a broad spectrum. So in undergraduate, I double majored with both chemistry and history because it was actually bringing in the way to analyze and look for details hidden amongst your first data sources, things like that you draw from in history actually help a lot when you're looking into a deep groove in a scientific field at the same time. So the irony is that the history degree actually is highly beneficial getting to graduate school and a PhD program and things like that in chemistry. Those skills actually paid off a lot. And it was then going on to graduate school and deep diving into chemistry work for me that I then transitioned into work in an analytical space. So I actually worked for the University of Illinois to begin with, running their mass spec instruments. And that piece ties in when we start talking about HVAC and vacuums and having understood those kind of systems in that pushing the boundaries of what can a system with vacuum do and how do you prepare a mass spec for being able to collect essentially the mass of an individual molecule really helps on, okay, we don't need to go to that level, but what are those general principles that applied in that setting that then can go into a real world setting that's going to help an HVAC tech in the field get better results, particularly as the HVAC equipment gets more and more essentially with smaller and smaller error bars is the easiest way to say that, of what it will tolerate versus decades before now, the HVAC equipment allowed for greater range of
A little slop, mistolerance, that kind of thing.
correct. And how you had it set up, that I would say that those error bars from my stance are getting smaller. And so applying more science-based approaches to those activities and techniques that I have historically applied in a lab setting and making those fit into a real world, not in a lab setting, is part of what we see as an important goal to move forward with.
There's that vacuum book that Bryan and Jim Bergman breathed into new life in the last year. Is that sort of along the lines of understanding those general principles? Would you say that book covers some of those things?
It does. It starts on a number of those. I think that it's a really good resource and a way for technicians to have some alternative perspective on what the vacuum and its importance and things are. It's been a while. I only read the historical version that Eric has.
The 1959 edition, right?
Yeah, I have not actually read the...
By the way, I'm a 1959 edition too. Did
Okay.
you know that?
Bill, that is the only version that I have read.
It really didn't change any. I managed to find the first edition on eBay once, and I bought that immediately just because I wanted one of the first editions. And there's been a couple of things taken out of it, but I don't think what Bryan and Jim did really changed the text of the book itself. They just cleaned up the illustrations and added another chapter is what they did.
Actually, I did the editing on the original stuff. It is 99% the same as the one you have.
Okay, so you did all of that
Okay.
then, yeah.
I wanted to be clear. I had not read the newest version, so I didn't. I'm like, I do not know.
Folks, in case you're interested, these two folks are the most honest people I know. So
And I just have to throw this out there. I mean, Rachel's education into science and chemistry specifically, I think, started even way before school because of her family's background in cooking, which, what's your favorite saying about cooking?
Chemistry is like cooking, only you get to lick the spoon in cooking.
I like that phrase.
That was where she really got started. And it's surprising to me how much chemistry really can be used in something as simple as cooking that we take for granted every day. She will start describing to me the interrelations of different oils and how they uptake. And blows my mind. And then I just realize how little I know about some topics.
Yeah, but it's also important that I then add that baking is where you have to apply scientific principles very robustly, but cooking, like making a soup or a lot of the things that you do like on a stovetop, are actually a lot more like jazz music.
Ah.
Okay, if we took another left turn.
But being very specific. So going back to the relatable aspects, and Eric, you talked about that's your specialty in this area. Lately, especially, you really developed that. I recognize that. But can you two help relate like vacuum level and the science and the vacuum level in air conditioning, refrigeration work? What are the measurement ranges?
In the sciences, they tend to go much, much lower pressure. And my way of thinking about vacuum is, yes, vacuum, it is pressure below atmosphere, but we're still measuring that pressure above the absolute zero line. But whereas she laughed at me the first time that I tried to describe to her how great we do in HVAC by pulling this 500 micron vacuum.
Yes, but you used the word deep.
Well, I did. I used a deep vacuum because that was what I was taught. And I was very quickly humbled and shown just how inadequate that really was when she says, yeah, what we call our roughing pumps does deeper than that.
The pumps that I have doing my chemistry work that literally only pull the vacuum on my glassware in my fume hood for just my day-to-day activities, pull a deeper vacuum than the vacuum pumps that the HVAC technicians carry around in their trucks. With good reason. My pump weighed a lot more and was not,
I was going to say portability.
Manageable. I mean, they were portable we could move them to go have them serviced, but they were not grab and lug around kind of situation. And that was where we started, was that level of pulling a vacuum in our hood. And so it was actually more not necessarily at all that the vacuum level we were reaching needed to be the same, but it was more on some of the approaches and thinking about how to come up and in a lab, do we seek out that we have a leak or those kinds of things, that there's ways to take those learnings and then apply them to the situations, tying the discussion, because we were just having about nitrogen, flowing nitrogen through your system and things like that, where you're using that to help sweep pieces out before applying your vacuum. And it's those kinds of dialogues that we have because, like for a mass spec, we flow helium to do the same thing. Because again, difference between the application in a science realm versus what you have in the HVAC, helium for us is that inert gas that we actually have to have, because in our very specified situations, nitrogen is actually reactionary. In the HVAC application, it is completely fine for nitrogen to be considered an inert gas with the exposure kinds of pieces that you have going and the levels that you're trying to clear to. So again, that's the difference. But the key of having that sweep of an inert gas, no matter how you define inert, is one of the important steps before you start pulling that vacuum that helps aid that pull down to be faster and not have this kinds of issues. And so then when you start getting to needing to pull further in things where we use bakeouts, we use different cleaning beforehand. If we have oil, for instance, in a mass spec, if you have a diffusion pump erupt, which sadly is known to happen, you launch oil throughout your entire mass spec. HVAC systems end up with oil and contaminants in them in the same way. So if you look at how myself as a mass spectrometrist went about trying to clean my system so it would go back to being able to pull under an appropriate level vacuum for that application and what had to be done, you can start to use some of those same pieces and logic and approaches to say, hey, would these in particular instances be helpful and applicable to being able to pull oils and contaminants out of an HVAC system?
So there are definitely parallels there. And bakeouts maybe heating a system, perhaps, Eric?
That's where they're heating the system up. We haven't gone too far down that road yet. I've got some ideas that I'm actually going to experiment with at some point, maybe to bring to technicians, but that's a ways down the road.
So talk about experimentation. Are there, behind that curtain, I'm looking at a video screen here, behind that curtain, are there experiments going on? Yeah, that one or another curtain? What's going on behind the curtain?
We are the ones behind the curtain.
Are you doing experiments like in your shop, your lab?
We do some things from time to time, yeah. It depends on what exactly is going on, but we run some different experiments with some things just to see what would happen. Again, that's what science is experimentation, having a theory, and then going in and, I guess, proving or disproving that theory and being willing to say, okay, this didn't pan out like I thought it would, or nope, that's not going to work. Yes, that is going to work. It's having a theory and having a goal simultaneously and say, does this achieve the goal?
Yeah, and that ties to that. Science is the pursuit of understanding in the moment. Because if you look across, again, like that historical timeline, you're talking about something that people like to use the word laws and truth. And, well, science said this is exactly what it's going to be. That's not accurate. Science is not a statement of facts for all time. Science is a statement of facts that are only facts for that moment until essentially it is a working theory always until we collect the data to disprove it.
And that also it's facts relative to the need, because some of the facts you talk about may not be the facts that Eric and HVAC technicians need to do their job. So they're not the absolute facts, but they're the necessary facts, again, in the moment too.
Correct. It's in the moment because, yeah, the inert gas is exactly a prime example of that way. If I'm in a chemistry experiment, nitrogen is not inert. But in an HVAC system, leveraging costs, real life, what it can and can't actually react with, it's inert.
I worked at a Superior Valve factory, and we would put in a ball valve testing equipment that used helium as the tracer gas to detect leaks because the helium molecule is so small. So again, this is on the molecular scale.
Correct. And yes, again, I use helium as a tracer gas in the science as well because it's the smallest. So you find the smallest hole.
And it's also easier to detect because it's not naturally occurring in the atmosphere. So you can have a very unique detector sensor, whereas like with our refrigerant detectors, where we get into trying to electronically detect refrigerant leaks, they have to be so broad because there's not one molecule type that they're looking for.
You lose accuracy. And most importantly, though, you actually lose the ability to detect at lower levels when you broaden in most cases.
Yeah, and you also lose the ability to define, and there's a term I'm looking for here, and it's just not coming to my mind right now. But basically, it's singling out whether or not that's actually a refrigerant.
Speciate, is that a term you might use?
You're looking versus accuracy and precision. You're going through it being precise on exactly knowing what entity it is. That precision is given up, even if it is accurate in that it's identified that there is a refrigerant leak.
Exclusion, that's the word I'm looking for.
Yeah, exclusively that thing.
Yeah, exclusively that one thing, because we have such a broad range of things to look for across the refrigerant possibilities that then we get cross-contamination with leak detection solutions and things like that. So we get that cross-sensitivity in there in a lot of cases. And it's the name of the game. It's going to have to happen because of the molecular makeup of the different fluids.
I think we talked a little bit about water and HVAC. That seemed to be the spearhead for this conversation. So I want you to talk a little bit about water in HVAC.
It's all wet.
And it's pretty much everywhere.
It is just about everywhere.
Water, I mean, if you drive at what we were talking about with vacuum, water's a key factor in trying to reach your goal or not being able to reach your goal when you're trying to pull that vacuum in a system. It's when it comes all the way up to the systems. And that's why our class on water, it was like we're only literally popping the top on all the different ways that water is an important and vital piece, not only to understand what is happening, but what you need to control across the whole HVACR space.
Yeah, it was an amazing, eye-opening thing to do the research that we did for that presentation at the Symposium. just to see all the different and various ways that water affects HVAC that I really hadn't even thought about, and even some of the ways on how it works and how it adheres to things, and especially when it's in a gaseous form.
And I mean, you tie in then water is both the most controlled as far as regulations on one hand, depending on the application, to going to be something that people just use everywhere and don't see it as being controlled. So it covers the whole broad spectrum from that standpoint. And so if you start to look at where it has government regulation tied to it and how that correlates with the kinds of things that you have on regulations coming and hitting things like refrigerants, there builds up a corollary between that where you need to start thinking about things on, okay, it goes back to that. How are they in a specific situation needing to be controlled, not just panning them as one or the other, meaning water is regulated if you label it as drinking water in a bottle, but it doesn't have the same regulation if it's sitting in a pond in your yard.
So what's the difference between those two?
One's actually controlled by the FDA and one is controlled by the EPA.
You
Okay.
can pee in one and you can't pee in the other.
Well, not and sell it afterwards.
Well, I thought you were talking about the P in EPA. There's a
well,
P in
there's
one.
that too.
There's that.
You mentioned something there, factor about surface adhesion. Did you say something like that? What was the interesting thing that came out when you started to explore that area?
Really, and this was actually started when I took one of Joe Stiebrick's building science classes in the fall of 2021. He started talking about adhesion onto surfaces of the water molecules and how that can affect microbial growth, especially, or the microbial growth, the organic growth that we see that happens on different surfaces if there's too much moisture. And I was very much prior to that in the camp of, hey, we got to watch dew point. We got to watch for liquid water forming on surfaces, as opposed to we just need to deal with higher relative humidities. And that was like, oh, this is why we have to deal with humidity, because as the relative humidity rises in a space, now this is going back to building science and controlling moisture in spaces more than in like under a vacuum. If we get high enough relative humidity, and it typically starts somewhere around that 75 to 80% relative humidity, we start getting enough adhesion of water molecules on surfaces that it's deep enough to support the growth of things. And then I'm talking to Rachel, and this is where we got into our personal biases. Well, when I look at a surface and I think that surface is smooth, and she thinks of that surface and she's looking at it with a microscope and it's like got cliffs and valleys and deep holes and all this other stuff. Well, when you start getting down to that molecular level, you realize that those water molecules stack up and they actually create little pockets in there, and it's a perfect growing place.
Long before you see the actual visual water in
Right.
a liquid form that people associate with, oh, this is why even on a window, this is why I could have mold problems. Well, you had that long before you ever saw that drop run down a glass or the frame or anything else.
Mm-hmm.
Let's explore that a little bit. Is there a way to detect surface or water adhesion on a surface?
Not easily, other than just watching your relative humidity in the space. Keep your relative humidity below that 75%. I mean, realistically, we want to keep the relative humidity in spaces between that 40 and 60. And in high humid times, I tend to keep it below 55% if possible. To me, the 45 to 55% is a sweet spot. If you start getting under 45%, you can drop it down to 40, but it starts getting really cold in the space, honestly, because evaporation will happen a lot quicker that way.
And when you mentioned adhesion on surfaces, I think you talked about the surface roughness, different kinds of surfaces.
Yeah.
Can you talk a little bit about the surfaces typical in HVAC? And there's the roughness on the Rachel scale, not the Eric scale.
So you're talking like inside of copper and things like that?
Yeah, inside of copper, on glass, painted wallboard,
Metal.
wood floors, metal, just a few different types of things we encounter in the typical HVAC real world.
Yeah, glass gets tricky, but it's probably one of the smoothest because it's actually still a liquid. So its surface is constantly changing.
Oh, wow. That's a big pause right there.
Oh,
Glass is a liquid and its surface is still changing.
Yeah.
yes.
Yeah.
I've seen actually proof of that, like looking at old buildings, like revolutionary type buildings, and you see the glass has sagged. It's wider at the bottom than it is at the top because it's still a
Moving.
liquid and still flowing.
Still a liquid.
It's still a liquid.
Wow.
Really thick liquid.
It's really, yes. So by constantly changing, it is not constantly like, it would be the same as 150 years ago, the speed at which you moved a piece of mail versus email now. So we're not talking about the now kind of timetable. It is something that takes a long time, but you're not looking at the same level of stagnation with the molecules in glass as you are in something
Like a metal or plastic or something
correct.
like that.
The thing that moves, and this is the part that changes the surface, whether you're looking at the surface itself, is that moves in all of them. So whether we're looking at the large movement that you can see over a very long time frame in glass, or if you're looking in that shorter now kind of movement, electrons are moving across the atoms, and that changes the surface from the charge that a floating by molecule sees, and that can change whether you get adhesion more quickly or it takes longer for it to build up. And so that part is constantly in motion with a material. And that's the piece where essentially, if we go back to water, as soon as you get one water molecule that will adhere to a surface, then you have additional charge and additional electrons available to attract more.
That's where you get cohesion.
So if you look at that, the surfaces being rough, essentially all the surfaces in HVAC I view as rough. If you put any of them under an electron microscope, which is the kind of approach that I'm used to when you look at surfaces, then they're all rough. I did work depositing layers for diffusion barriers on semiconductor chips, and we did work with lots of acids and things to actually smooth the surface of the chip. So you're talking about a silicone wafer. That's the type of thing that after prep, I consider smooth. Because we then analyze those and make sure that that prep gives us a smooth surface. And there you're looking at only a couple of molecules differentiation. Whereas, again, this is where the applicability, that level of smoothness is not required, needed, or achievable when you get to the real world with the HVAC pieces. And so, like you're talking about glass, there's films and other chemical materials that get made that can be put on there that whether it's on the glass itself, like on a window, or on the framing material that change its smoothness more or less. But those all add costs. So if you are trying to drive to a very tight expectation of when you want that to be formed, or if you have a lot of issues with it, then it would be potentially worth investing in putting additional surface controls in place that would change that to a closer to a scientific smooth surface than a traditionally.
Again, depending upon the need and the application.
Correct. And that's the only time to me that you would then move to that.
Yeah, when we're talking about smoothness here, we're not talking about like even 8,000 grit sandpaper. That's not smooth still.
And what I'm hearing here, there's a lot of interesting things going on about relating these two worlds of HVAC science and laboratory science. Traditional science in terms of time is all relative, size is relative. And when you talked about like attraction, like we think of water resting on a surface, but you're talking about molecular attraction, which operates on a totally different scale with different mechanisms going on. Can you talk a little bit about dirt on surfaces from like an HVAC standpoint? That's really important for maintenance. What about it from a chemical standpoint? What's going on that causes dirt to adhere to surfaces?
To a rough, molecularly rough surface. Right?
I mean, a lot of times actually with dirt, it comes back to the fact that you already have water on there.
Okay. And then is the water like the electrical, what'd you call it?
Yeah, because what you have is you have a charge. Once you get some molecular water on a surface, it helps water because of the polar nature of water. It drives to a significant charge on your surface. It's the same reason that people are going to be more familiar. If you watch like an insect, they can sit and land on water and they appear to float. It's actually comes all the way down to the polar nature, which is the charge of the water molecule. So if you take that concept that you can see when you watch an animal, insects typically, land and appear to float on water, that piece, when you translate it to the molecular level, if you have water adhered on a surface, no matter how rough or smooth, that helps to amplify that charge on the surface, which then attracts dust particles. They all have charge as well. You get enough dust, it then appears as dirt. So anything floating in your air, so whether you're going all the way to VOCs, any of those that we don't typically think of as dirt, those are usually differentiated, but you will actually start to build up those organic compounds because they also often carry a charge across them.
And from the standpoint of charge, is it a very simple, like large scale physical world, talking about scale and size? Is it like magnetism?
Yes. It'll work very, very similarly. Yes. It's still the very same principle of what we got taught of negative. The one side of a magnet is attracted and the other is repulsed. Works the exact same way. It's why magnets are actually always identified the same as our batteries, the positive and negative. All of those in that macro scale work on the micro scale. That positive, negative is still the approach that you leverage across that spectrum.
Got it. Macro versus micro. I like that. Now, one more topic. We're going to just blow our listeners' minds just a little bit more, and then we're going to wrap up and just leave them hanging for the next time we get back together. So this next topic is on filtration, air filtration, and the scientific aspects of how filters work. Who wants to talk about that? They're smiling at you out there.
A lot of times when we think about air filtration, we think of literally what's called exclusion, which is where it kind of acts like a window screen. And you can push certain sizes of things through a screen and other things just get caught in that screen when you try to blow it through them. Now, that's big stuff that we can see.
Like pasta strainer kind of thing.
Yeah, that's the strainer.
But we have the same in science. We have size exclusion, filtration, all to the molecular level, where you choose which size you want to actually go through. That's actually a part of purification when you go through that, depending on the process you're building out.
You can build like a gate to certain size molecules.
Correct. You actually do that. You build your filter to have size exclusion capabilities in the same way, just on a more micro scale of what it is that you're...
Smaller window screen.
Correct. Really tiny window screen.
You can't get that at Ace Hardware.
I've seen some illustrations but there's other mechanisms by which filters work, and that does involve polarity.
Yes, that is correct. So the next piece, typically, like from a science standpoint, and I know that there's some applications as well, where you start using charge.
Most air filters, especially high MERV air filters, are going to use this method where they actually charge the media, and that even some of your lower MERV units use that. That's where we get the recommended change duration on those air filters.
Because they get coated?
Well, because their charge will be, the estimation is that the charge will essentially be used up.
And that actually applies the same way when, again, going back to that purification approach, we have what we call resins, and they hold a given charge to help that separation out step and we have to recharge those resins after a given. We know and do all the testing to say this is how long that resin can last to pull X volume going over it. So, I mean, it's the same, again, general principle that you then tweak to being, here's a homeowner that can actually just replace this filter because the testing's already said this is how long with a given volume of airflow within air.
And the reason that we do that is simply to try to get lower pressure drops across filters, because blowers don't care. This is one of my pet peeves. A lot of our filters are rated in feet per minute of velocity. And I have yet to find a blower that moves air that cares how fast the air is going. They care about resistance to airflow coming into or going out of that blower? How much resistance do they have to work against? So one of the reasons that we use charges on filter media is because it allows us to capture the charge of the media, allows us to capture those smaller molecules without making holes that small to use the exclusion method.
So it's a combination of things.
Yeah.
I'm going to ask a question about charged resins, back to Rachel. I believe that's what's happening in my water treatment tank for well water.
It very likely is. There's a lot of different ways to approach that water purification. Typically, it's a kind of this purification that I've been talking about. When it comes to water treatment, you usually have multiple purification steps in place because size exclusion is often one of the very first ones, even when it's just gross size exclusion or macro from what you're trying to take out in water. So you then normally end up with a resin-based that does drive to being able to pull based on charge. It just changes. So if you have something like an RO system, it's one of the most common available.
Reverse osmosis.
Yes. Yeah. Sorry. Reverse osmosis. Thank you.
She's all in on the abbreviations for everything.
Yes, sure. You got to be. Otherwise, we'd be here for hours.
Alphabet soup is my skill set. You look at that, you end up putting cartridges in like a commercially available to your home system. Those cartridges have different resins across them based on what you have prioritized on top of just the reverse osmosis steps for your water purification you want to have happen. And so it's the same. Again, that principle of dialing into what's important for that water that you're wanting to have come out of that system and how you want that purified translates to the same thing that we're talking about of take something and dial it in to where that application is applicable and what those, I call them user requirements, homeowner needs, how you want to expand on that is still the same approach of knowing what that user needs is then what allows us to have and build on these conversations every time.
And that's interesting because before we started recording, we talked about the fact that you're working together to increase relevancy towards the beneficial actual goals. And that's exactly where you ended. This is perfect.
It's all about setting the goals because then you got some place to head.
I really appreciate you coming on the podcast and bringing to light a lot of these more intricate matters. And it's so cool that you're working together to do this. What can we look forward to next from the Rachel and Eric show?
We've got some stuff under our hat, but I think now we're going to keep that under our hat. But there's some stuff.
Nice.
Micro and macro.
Yes.
Of course. Relating to some terminology we use. Again, thank you for coming on the Building HVAC Science podcast. Really look forward to having you back. And when you're ready to talk about more, I'm open to it.
Thank you, Bill.
Thank you very much, Bill, for having us on. It's been a lot of fun.
Good. We love it. Thanks. I'd like to thank you for listening to this episode of the Building HVAC Science podcast. If you want to keep up with other things we find interesting, follow us on Facebook by searching for Building HVAC Science in the Facebook search bar. There are other trade-related resources and influencers that we follow, and that's the HVACR School with Bryan Orr, Zach Ciota of HVAC Shop Talk, Stephen Reardon, HVAC Reefer Guy, Tool Pros, Service Business Mastery, Quality HVAC, HVAC Overtime, HVACR Videos, and Grayson Corbett Lunsford at HomeDiagnosis.tv, the first TV show on home performance. And of course, the always interesting and entertaining Jim Bergman on the MeasureQuick YouTube channel. Again, I want to thank you for listening in today. The Building HVAC Science podcast is a production of True Tech Tools Limited. Until next time, take care.